Can you hear us now?
I cannot for some reason.
Again, wait.
Okay, looks like we're having technical difficulties.
Can you hear us now?
No.
Yes.
The audio is going to the
Close the door.
We're good? Okay, maybe let me reintroduce Mayank again. So welcome everyone for another session of Safari live seminar. So we are pleased to have Mayank here. So Mayank is a first year PhD student in Safari Research Group working with Professor Onumutlu. And before joining as a PhD, he was in IIIT Bangalore doing his integrated masters. And his research focus is primarily revolving around privacy preserving technologies. Like one example you're going to see in homomorphic encryption, and to accelerate these technologies using near data processing, near storage processing. So Mayank is going to discuss about his recent published work called CIPHERMATCH, and stage is yours. Just before starting, the folks who are joining online as well as through YouTube, feel free to ask your questions, and we are going to convey this to Mayank at regular interval. And yeah, hope you all enjoy the presentation. Mayank.
Thank you. Thank you for the introduction. Hi everyone. So today I will be presenting our latest work, CIPHERMATCH, accelerating homomorphic encryption-based string matching via memory-efficient data packing and in flash processing. And this work was published in recent ASCLOS 2025. So let's briefly go through an executive summary of this work. So the problem that we are targeting is secure exact string matching using homomorphic encryption. It lacks scalability due to performance bottleneck in two key areas. First is the use of complex homomorphic operation. For example, if you have to perform string matching, you have to do homomorphic multiplication operation, which results in high computation cost. Also, there's a data movement bottleneck because homomorphic encryption leads to large encrypted databases, which are usually stored in your solid state drives, SSDs. Our goal is to develop an algorithm hardware co-design to provide scalable, parallelizable, and efficient homomorphic encryption-based secure exact string matching. And our key idea is that if we can eliminate the use of homomorphic multiplication, so we use only homomorphic addition, and we perform in-flash processing by exploiting the operational principles of NAND flash memory, so that we can accelerate and remove the first two problems, and we accelerate the secure exact string matching. With this, we propose CIPHERMATCH, a new algorithm hardware co-design that significantly improves the performance of HE-based secure exact string matching by using only homomorphic addition, which reduces high computation cost, optimizing the data packing scheme so that we can reduce the overall memory footprint, which happens due to after homomorphic encryption. And we design a new in-flash processing architecture so that we can reduce data movement and use this proposed algorithm, and we accelerate this algorithm using in-flash processing. Our CIPHERMATCH algorithm provides 42.9 times speedups and 39.4 times energy savings over the current state-of-the-art algorithms. And when we implement CIPHERMATCH using in-flash processing, we further see a speedup of 136.9 times and 256.4 times energy savings over our CIPHERMATCH software implementation, which is running on a standard conventional CPU system. This is the talk outline, and we will first briefly go into the background problem and what is our goal in more detail. So exact string matching is used in many security critical applications, such as databases. For example, if you want to search a query in a sensitive databases, or bioinformatics, for example, identifying similarities in DNA sequences. Now, let's assume a scenario. For example, you have a user, and a user has its own query. Now, the user has his database encrypted and stored in a conventional string matching. User has a database which is stored in the server in the SSD. Now, on this database, the user will send the query on the database, and then the user will perform a match. If the match exists, if the user finds a match on the server will send the result back. Now, performing computation on simple conventional data, on a plain text data, can lead to a data leakage. For example, the attacker can see your computations, whatever you are performing on the CPU, so that you can actually get to know what exactly is your data. Now, homomorphic encryption is there so that it can be leveraged to perform secure exact string matching, so that you hide all the computations that you are doing using the homomorphic encryption mathematics, so that you don't leak or convey any data to the attacker. Now let's see how secure exact string matching will be done. First, the user will encrypt the query, and then he will send the encrypted query to the server. On the server, we will have our database, which will be encryptically stored onto the storage SSDs, and we will perform homomorphic operations. Now, in homomorphic operation, it allows users to compute on encrypted data without decrypting it. So you can actually have the encrypted data, you perform some mathematical operations which are proposed from homomorphic encryption paradigm, and then you can evaluate whatever the function that you want to do. And then finally, you send back the result to the user, where the user can decrypt the result and can see your final answer. Now let's see an even more detailed example how exactly it will look like. So user has its first in a scenario. Let's assume a simple scenario. User will have its own database. For example, my specific sensitive database of, let's say, financial databases. I will have this database in a plain text format. In my own host system, I will encrypt it. Now I have written a parameters there. So this encryption requires a set of parameters that needs to be used to convert it into some random value which will not be known to anyone. And these parameters, for example, let's say A1 and E1. Now we encrypt the database, we store it to the central, let's say, for example, a cloud server where we store this encrypted database into the storage system. Now we have our encrypted database. Assume the user again has its query, and the user is going to encrypt the query with the next set of parameters, which will be again sampled in the host system. For example, A2 and E2. Now, even if you have more number of queries, for example, 10 queries, you're going to sample these parameters every time, and then you're going to send it to the cloud server, so that every time with the query, the encryption looks different, so that you cannot figure out anything, whatever is happening. You cannot figure out anything from the encryption if you can perform a brute force attack, like sending the same query multiple times. So you send this encrypted query, perform some computation on the cloud server, where you perform string matching exactly for our scenario, exact string matching, and then you send the result back to the user, where the user can see what exactly it's happened. For example, you can see whether the result of your query does exist in your database or not. It's like an answer of yes or a no. Or you can figure out what index where your query exists. So you can do all sort of these things by homomorphically and using homomorphic encryption. Now, the one point that I want everyone to note here, that we have E1 and E2, which the parameters that I talked about. These are called as errors. Now, these errors can go out of bounds, which I will explain in later slides. What does it mean? Means that just a very brief idea that you want to perform some computations on the encrypted data. Something will happen to these A1 and A2 and E2, so that E1 and E2 can grow bigger after, let's say, for example, performing multiplication or addition or any other operation. And it can go out of bounds, specifically after performing homomorphic multiplication operations. Now we will see why it is a problem in our future slides and what prior works lack here. Now for our future slides, we are going to assume this scenario, that our client system where we can encrypt the data, and the cloud system or the server system where the database is stored. So now secure string matching using homomorphic encryption can be performed using two key approaches: by using a Boolean approach or by using an arithmetic approach. For example, in the Boolean approach, we will have individual bits of your data or database or query, and you will perform homomorphic XOR and AND operations to find out the exact matches. Whereas on the other side, you will take multiple bits, you will pack them, where I will explain what packing means, and then you will perform homomorphic multiplication and addition operation. For example, you can calculate Hamming distance between the bits, so that requires you to perform homomorphic multiplication and addition operations. Now, there are several advantages and disadvantages of both the approaches. Let's look at it. Now, in Boolean approach, we have taken each bit. When we take each bit and encrypt it, it's the footprint of that encrypted data is going to be very huge. And that's why we'll have very high memory footprint due to encryption of individual bits. Whereas on the other side, as you take multiple bits together and pack them, for example, a set of 32 bits, and then you encrypt it, you have lower memory footprint as compared to Boolean approach. It is because of the data packing mechanisms. Now, as you have the individual bits are encrypted, you have to perform large number of HE operations because you have one bit encrypted as an encrypted data, and you have to perform costly homomorphic operations, for example, XOR and AND operations. Whereas on the other side, arithmetic approach, as you have less number of HE operations that you need to perform, that's why you see a lower computation footprint as compared to Boolean approach. But there is a trade-off here, another trade-off. As Boolean approaches, these Boolean approaches are recently explored in 2017 or 2018, where they optimized the homomorphic encryption and all the algorithm so that you can perform any number of homomorphic operations. For example, you can go as deep in your circuit to perform XOR and AND operation. And that's the reason why Boolean approaches can support flexible query sizes. So you can go as deep as possible. You can perform XOR of in bits in parallel, and then you can reduce by performing as many AND operation as possible. Whereas in arithmetic approach, you are limited by this query sizes because homomorphic multiplication, now as I explained in the previous slides, the error E1 and E2, they easily go out of hands. And then homomorphic multiplication, when you perform homomorphic multiplication, you can see that E1 is going to scale up, and after some point you cannot decrypt back your result and get the correct results. And that's why they support only limited number of query sizes because of this homomorphic multiplication. So there are trade-offs between both the schemes. There are more detailed analysis in the paper, whereas there are prior approaches on these HE-based secure string matching, for example, both in arithmetic approaches and in Boolean approaches. But for this session, we will focus more on arithmetic approaches, how the arithmetic approaches are usually performed and how can we improve them. As we see that in our previous analysis that arithmetic approaches have lower memory footprint and lower computation cost, but they have a problem that they cannot be scalable to any flexible query sizes. Can we do even better? So that's why we are going to focus on these arithmetic approaches more from now on. So let's look into a more detailed on this arithmetic approaches, how they perform.
Question.
Yes.
So arithmetic approach seems to be another way of doing the same computation as a Boolean approach, right?
Yes.
So, and clearly arithmetic approach gains a lot on its own side,
yes,
right? Due to low footprint as well as low computational cost. So why would anyone prefer to go for Boolean approach?
Yes,
that's one thing. And then the second thing is that it seems like the citations that you showed as Boolean approach, they are also pretty recent. So
yes,
I'm assuming that these Boolean approaches are explored recently.
Yes.
So what is something that is so fundamentally lacking in arithmetic approach that made the researchers to go for Boolean approach? I'm not sure whether this is a scope of this presentation, but
I can answer it at a very high level. Yeah. So basically, when homomorphic encryption and algorithms were proposed early back in 2011, for example, now they were looking at how can we perform these arithmetic operations, for example, addition and multiplication. And there are specific schemes. For example, recent works have explored that you can pack a lot of data. You can perform bulk multiplication or bulk addition. Now, these will be used for performing your, let's say, machine learning applications very efficiently. Not, I mean, not as compared to normal computations, but they will be still better. But let's say if you have to perform any arbitrary circuit computations, for example, circuit gates of AND and OR operations, what will you do? The conventional way to do it is basically you will take one bit, encrypt it, then you will perform homomorphic multiplication to mimic an AND operation. So because multiplication of 2 bits is an AND operation, and addition of 2 bits is an OR operation, right? So you will perform homomorphic multiplication, and the footprint after 1 bit, when it is converted, we have done experiments and we have seen that the memories, after 1 bit can be converted into a 3.5 megabytes of data. Now you don't want to perform on 1 bit. So that's why the other scheme, the Boolean approach, was proposed so that you can perform all these operations like any like for example 1 bit operations more efficiently. And that's why they were recently observed in 2017, 2018. And nowadays they are exploring for the applications of it. For example, string matching is one application, because you have to take, let's say, a 256-bit query is present. For example, you will do an XOR operation which is in parallel, but you have to reduce back. So now you cannot reduce back by taking each bit and encrypting it and then performing multiplications, right? There should be much better way. That's why these schemes are proposed. Boolean approaches are proposed. And that's why we are seeing they are in, like latestly, they are evolving more and more with more and more applications that they are discovering. Yes.
Makes sense.
Thank you. Any other questions? Yes.
In the slide 14, you
Yes.
said that we encrypt the message using two different errors.
Yes.
So how, and two different A values.
Yes.
Then how can you, like, because after encryption, the ciphertext would be different. So
Yes.
still, how can you efficiently perform?
So that's the proposal of this idea that we are going to use. Just a hint here that you can, that homomorphic, so homomorphic multiplication is very complicated, whereas homomorphic addition is a bit simple that you can observe. And you can observe that there exists a homomorphism after when A1, A2, A1, A2 and E1, E2 are used, so that you can construct actually how how the result and encrypted with E1 plus E2, because we are using addition only. So E1 plus E2 will look like. So we will see in the later slides in much more detail how this algorithm will work. Any other questions? Okay. Okay, so we'll look into more into how arithmetic approaches are done. So we take, for example, we have databases. Now we will take multiple bits of these data. We will take, so we will take multiple bits from the data, let's say a chunk of it. We'll place the individual bits into, let's say, a vector. And these vectors, so you can see these boxes as basically the elements in a vector, and you will place each bits here. Now this will construct your, you can see that this vector can be called as a plain text. And you can consider this as a polynomial. I will not go into more details of how polynomial is, but you can see that this is the highest degree coefficient of the polynomial. This can be the lowest degree coefficient of the polynomial. Now, you basically what you perform is you perform encryption on this plain text. Now you have encoded the database and you take multiple bits and pack it. You encrypt the database. Now, how you do encryption is individual bits. Like for example, this element of this vector was 1 bit. Whereas after encryption, element of this vector will now constitute of 32 bits. And another factor is that it's going to make from 1024 elements, for example, to 2048 elements. Now I'm not going into detail why 1024 and 2048 elements are used, because that's the homomorphic encryption property that we generally use these high degree polynomial, for example, 1024, 2048, and then we represent our data like this. Now, as you can see that we have, if we have a kind of 128 bytes of a conventional database, once we encrypt it, it's going to become an 8 kilobyte, which is an increase in 64 times. Because as we can see, 1 bit can convert into 32 bits, and we have like double in the vector of that polynomial. Now we have in prior work 64 times memory increase. Now this is for memory. Now what let's say we represent this as an encrypted database. We represent our encrypted query. Again, like we have our query, what we can do is we can represent our query like this. We encrypt it so that our query is like this. We replicate this query so that we can parallelly perform our search across the encrypted database, and then we perform some set of homomorphic operations. For example, we will perform a homomorphic for example, for calculating Hamming distance, you have to perform two homomorphic multiplication and 3 homomorphic addition so that you can calculate your Hamming distance. And then finally, we will see this encrypted result. And this encrypted result will be result after your function, whatever you have called, for example, your Hamming distance function. Now, we analyze the execution time of these arithmetic. Yes.
Can you get back to the slide about memory footprint increase?
Yes.
So this 64 times increase is for arithmetic approach.
Yes.
So what would be the size for Boolean
approach? So you can.
You're still packing, right?
Yes, I'm still packing. I'm still talking about the arithmetic approach.
Okay.
Whereas in the Boolean approach, what will happen is, for example, you will have 1024. Yes, 1 kilobyte. So for example, 1 bit will be converted to 1 kilobyte bit.
1 bit?
1 bit will be 1 kilobyte, because you will take 1 bit, you will encrypt it. That encryption scheme is a little bit different than arithmetic approach. So what I said, like 1 bit will be gone to 3.5 megabytes of bit in arithmetic approaches. Whereas in Boolean approaches, 1 bit will go across, let's say for for example, 1 kilobyte, 2 kilobyte based on your schemes. And then you will have like 128 bytes, then the database size will be like very large. Yes.
And what's the trade-off on packing? Like if you pack more bits, what would the effect?
So we can also assume that this is one of the approach that prior works have used. Now, why they packed one bit is basically you will have one bit in this whole element. Now, this is constructed as a basically an element, or let's say a coefficient of a polynomial. Now, this is the lowest degree, for example, x raised to power 0. Now you have one bit here, which is represented as an encrypted bit. If you want to perform multiplication with something else, that will be a 1 bit to 1 bit multiplication. Now, if you represent 2 bit, that will be a 2 bit multiplication, how it will be done. Now, that cannot directly relate to how string matching will be done, because they want to perform an AND operation on bit by bit. So there can be much more efficient packing schemes, but which are not yet explored. The prior works are looking at like how can you pack it. They have their own disadvantages also. Then they look at how can they become more scalable across the SIMD architectures and the details like that.
My question is about the number of bits that you pack. Is it fixed?
So for this approach, you can pack one bit in one coefficient. For this scheme, you can actually go up to, for example, if I take one example, if your polynomial is degree 1024, you can actually go up to 14 to 15 bits in one coefficient. And then encrypted data will actually become 32 bits. So that's for one scheme. There are other schemes like 2048, which you can go even higher. But as polynomial grows, the computations grows itself. Yes.
And what is so in the database, you're
Yes.
kind of clustering different, 1 and 0.
Yes.
Like different groups. So what are these groups?
So basically, if you spread out the database as a binary string,
yes,
for you. Now, what you do is you basically take chunks of bits. For example, the vector length, vector size for 1024. So you will take a chunk of 1024 bits,
okay,
and you will spread out one bit into the elements.
Okay. And that has nothing to do with packing scheme.
This is also one of the packing schemes, because we are packing 1024 into one coefficient, one vector, which will be converted into an encrypted one polynomial. Okay. You can also have only one bit, just one bit. You can just place like 0 values here. Then you encrypt it. That will also become an encrypted value, but this will be of only one bit.
So this can turn to Boolean.
This can turn to Boolean approach. Yes.
I wanted to understand. Okay, great.
Okay, thank you.
So I have one
Yes.
question on this. So maybe actually question from that side, you actually want to repeat the questions, because I'm not sure how much
Okay,
it's going to,
yes.
but from
next.
So 128, so you are packing some specific number of bits, right? How many bits? 128 bytes.
For example, you can take 1024 bits for a very simple number.
1024 bits.
Yes.
10, 3, 128 bytes. Yeah.
For example.
So what is limiting us from, so why that 128 bytes?
So I can only pack 128 bytes. Why cannot
Can we go more?
Yes. So that's the thing. So in this algorithm, when I say in this algorithm, you have to calculate Hamming distance. Now, when we are calculating Hamming distance, what you do is you take bit by bit, and then you calculate the Hamming distance of that, right? So that's why we take one bit and place it into the coefficient of one polynomial. So you can assume this as a polynomial, a degree 0, and this is degree 1024. Now this is going to be one bit for you. And then you will perform bit by bit Hamming distance for you with the query, for example, right?
Okay. That's the plain text, right?
So yes, so this is the plain text. So the thing is that if you can perform any function in your plain text which can represent as addition and multiplication, you can just simply call it as homomorphic addition and homomorphic multiplication operations, right?
Maybe my question was not clear. Maybe like why 128 byte? Why not
256 byte?
Yes, I mean, what's that number coming from?
So 128 byte means 1024, right?
Correct.
So we have 1024 bits. Now this polynomial, this is a vector. There are 1024 elements in it. Now what you can do is you can take 5 and 2 elements and pack 2 bits into each thing, right? And remaining one you can left out, or you can pack even more, for example, right? Right now what is done is you have packed one bit. Now why is that? That's what I'm saying. This a 1 bit is going to come into the encrypted domain the once you encrypt it into this specific element. Now you can, once you have this element, this is a random value for you, this element. Now you can take this element and perform some computations, right? Whatever you will do will be on.
So you are essentially saying that the size of the packing that you are doing is dictated by the polynomial degree.
That's true. Yes.
Is that what you're saying?
Yes.
So if I go for higher degree polynomial, then I can do that.
Yes, you can pack more. So
is there any reason why we would choose?
No. So this is okay. Sorry for that. So because I just explained it as a very simple example of 1024. The degrees that we use conventionally in our homomorphic encryption start from 40968192 and goes up to 632768. So you can actually take more data and then pack it. But it comes with a trade-off. If you have smaller size, the computations will be performed on this polynomial, which is degree 1024, will be a bit faster as compared to a degree of 32768, right? Because that's a large polynomial. If you have to perform computation, let's say some polynomial multiplication operations, that will be much more complex, and it will be more time consuming as compared to the other approaches. But on the other hand, you will do more computations because you have more data with present. So it comes with a trade-off. What type of operations you need to perform, how much data you can pack. I will give an example, like for machine learning applications, they actually go as high bits, as high polynomial multiplication as possible, so that you can perform as many parallel multiplication as possible.
Yeah, I mean, a naive way of thought process is to pack as much as possible, right? So that you can extract the maximum amount of vector execution.
Yes, that's true.
Okay, yeah. So I mean, that was the rationale behind this question, like why 1024? Do we see if we go for, let's say, 2K or let's say up to 32K, as you said, right?
Yes.
So do we see this trade-off moving somewhere, and then the observations that you are taking it out from this discussion, does those observations change also in some way? That was kind of the obvious follow-up, but I understand. Well, maybe we can just continue.
Okay. Yes.
If you are packing 1024 bits, the resulting polynomial would be of degree 1023, right?
The degree of this will be 1023. Yes. Okay. Yes. Like basically, this will be x raised to power 0, and this will be x raised to 1023. Okay. Yes. Any other questions? Okay. Okay. So then next, after understanding these arithmetic approaches where they are performing homomorphic multiplication and addition operations, we analyze the total execution time of one of the prior approach, which is best in terms of performance, although it comes at other trade-offs, but we are not going into details for now, but we will take it as the best performing prior work to perform secure string matching, and they are performing Hamming distance calculation. We observe that 98% of the total time it is taken for performing homomorphic multiplication operations. And this also follows by experiments that homomorphic multiplication is actually 100 times slower than performing homomorphic addition. And because like this prior work was using only 2 operations, homomorphic multiplication and additions, and using it to calculate the Hamming distance, homomorphic multiplication is 100 times slower on a conventional CPU system. Now it will remain, yes.
Yeah, maybe you were saying what I wanted to ask, but how does this breakdown look like if you use some accelerator?
Yes. So basically the homomorphic, so if I go into much details of the algorithms, homomorphic addition is basically performing polynomial addition. Now if you can assume 2 polynomials, you add them, they have a very high SIMD, you can actually exploit very high SIMD parallelism, and it's just performing let's say 64-bit addition or a 32-bit addition. Whereas performing homomorphic multiplication, you have to take polynomials and perform polynomial multiplication, which actually involves taking whole vector, multiplying with each coefficient, and it actually scales to order n square. Whereas homomorphic addition is order n. There are works which have improved homomorphic multiplication on order n log n by utilizing the techniques like fast Fourier transform or number theoretic transform, but still it remains a bottleneck in these systems. That's from the computation sides. I will also come from the another sides that data movement is also another bottleneck, which I will come in the next few slides. Yes.
I think okay, but I think what Mohammed asked, like this is the breakdown.
Yes.
When you are looking at the execution latency in a CPU system.
In a CPU system,
So
yes.
if you have an accelerator,
Yes.
which is already accelerating everything.
Yes.
So that blob of 98% would contribute less.
But then that block of 2% also will be much less, right? Because you will have a, let's say, an accelerator of performing a.
Yeah, but I think multiplication can benefit more because your CPU you can use the CD extension of CPU to accelerate addition, as you also said.
Yes.
But you cannot use them easily for homomorphic multiplication.
Yes, that's true.
And that's why when you use accelerator, you're gonna see much better boost.
Yes, that's true. That's true. It's going to be much better boost for sure. But homomorphic multiplication will still be slower than performing homomorphic addition. That's the fact, because you will have to perform, even if you break down everything to performing one multiplication versus one addition, one multiplication is going to be slower than performing one addition of, let's say, 32-bit number, right? So that's what I'm saying.
So how many so so you talk about the order, the big O of homomorphic multiplication, which is O, I mean it can be n log
n.
And for addition it's okay,
ON, yes.
But what's the number of multiplications and addition that you are doing?
In this approach, or in general you are talking?
In arithmetic approach.
So yes, in arithmetic. So for example, in this work, what we are doing is we are performing 2 homomorphic multiplication and 3 homomorphic addition to perform.
So they are not order like.
So each homomorphic multiplication is order n log.
Sorry.
So each homomorphic multiplication is order n log n. Now you have 2 homomorphic multiplication and 3 homomorphic addition to calculate a Hamming distance for you.
Okay.
Yes.
I think that makes sense. So you don't have order of magnitude higher number of additions. So in the end, they are.
Yes, exactly. Yes.
There can be some cases that you do, for example, 1 order of magnitude more addition.
So that's again also going into, for example, if I go into a bit more detail at very high level, for example, you are performing 5 multiplications and 100 additions.
Yes.
A 1 homomorphic multiplication. If I take CPU system, for example.
That's out of my question.
That's okay. Let's take like, for example, 1 homomorphic multiplication.
I mean, if you do a theoretical calculation,
yes.
So n log n.
Yes.
For n equals 1024 comes to be 1024.10, right?
Yes.
And order of n is coming to be 1024.
Yes.
So you are actually seeing a 10x increase theoretically, right?
Yes.
Theoretically, your multiplication can cause 10x more,
yes.
right? Now you need to have 10x more addition to just break even.
So if this is assuming that homomorphic, so addition and multiplication time is actually same, so then it's makes sense.
No. So I already counted, right? So if your addition time is, let's say, x, right?
Yes,
your multiplication time would come at 10x for 1024.
So that's the order, right? So each multiplication will also be much costlier than your addition.
This is not costing for multiplication itself.
We are considering the big O.
So big O of n log n.
It's a kind of estimation, of course, but
okay.
We are doing some
theoretical analysis.
It's a theoretical, right? So big O of n log n, when n is equals 1024, is coming to be 1024.10, and big O of n is coming to be 1024. So we are already seeing a 10x difference. So the question that probably one can ask is that if you see that the count of multiplications or let's say count of addition is 10x more than multiplication, would that kind of break even? But maybe we can take another question.
Yeah, you also have to do relinearization operation, which is also very costly. So it's not only the multiplication you're doing, you're also doing additional operations, which are even more costly.
So in this breakdown, is relinearization also included or bootstrapping also included, or is it just
It is just multiplication for now. So another thing that I want to explain is that we just saw that that addition, when you want to perform homomorphic addition, when we see the encrypted data, it becomes 2048, right? The encrypted data, which is degree of 2048. So basically, it is actually two polynomials of degree 1024. Now, when you perform addition, they remain two polynomials of degree 1024. When you perform multiplication, we start with a two polynomials of degree 1024. They become three polynomials of 1024. That's a homomorphic multiplication operation, how it is done. And now you will say that if you have a lot of multiplication, it's not scalable, right? It will not go because you will just increase on the number of polynomials that are going to go. So that's why what Philip was saying, that we have performed relinearization operation, which actually reduced back from this 3 degree back to 2 degree. So it also has a cost itself of relinearization operation, which also adds up on homomorphic multiplication. So it's not a direct comparison, I will say, from n log n and then saying order n and then we scale up additions by 10 times. It's not a direct comparison, I will say. It will go into much more details of how homomorphic operations are done. Yes. Any other questions?
Good to look into this breakdown in more detail. Like there are some operations that you're kind of ignoring or omitting in this breakdown.
Yes.
Also, I would like to see the breakdown when we have accelerator.
Okay, that can be something that we can do on top
and
of
also
this.
If there is kind of application that we do more addition compared to, like you say that we do 2 multiplication and 3 addition,
Yes.
so they are not that much different.
Yes.
But if you do, for example, 2 multiplication and then 20 addition,
yes,
then
then yes, we can. Then yes, I cannot say directly what will be the direct comparison. But yes, as like just fundamentally thinking, if you just increase addition, at some point it's going to go.
No, is there a kind of application on top of your head?
Not at this moment, at this time. I can think like what. So currently, these homomorphic operations are used in machine learning.
Hamming distance calculation.
Yes.
And Hamming distance calculation is kind of is actually okay. Is used for this string matching? Or
yes, it's used for string matching.
So in this context, I think that.
Yes, so that's so. This is the analysis of only this work. This is a general analysis of homomorphic multiplication being 100 times slower than one homomorphic encryption as compared homomorphic multiplication as one homomorphic addition.
Yeah, that's for CPU system.
Yes, for CPU system. Yes. What will happen for other systems? There are works which have evaluated for GPU systems what it will do, and then there are more ongoing works in ASIC side, FPGA sides, and then more on near data processing.
What about F1 accelerator?
Yes.
Do you know the comparison?
So I don't remember the numbers of that.
I think yeah.
Yes. Okay. Any other questions? Okay, thank you. Okay, so for this application, okay, I will be more specific now. So for this applications, what we observe that homomorphic multiplication, it limits the scalability of these HE-based string matching operations, string matching algorithms. Now that's our first key problem that we are targeting, that can be somehow eliminate or reduce homomorphic multiplication operations. Now, second is, as we are looking at string matching on databases are usually large and they are stored in the SSD system. And when you perform homomorphic encryption, as we saw, they will further increase the database size. Now, with this, the data movement between your encrypted data will become too much. And then now you can think that I'm coming to the data movement bottleneck. The data movement is now also another major part that contribute into these kind of algorithms that we use. So let's look at the different processing paradigms very quickly. So there are compute-centric systems where we perform computations in CPU and GPU, but they are restricted by the memory bandwidth or the storage IO bandwidth, because if you have very large data, for example, in terabytes, these channels will be the bottleneck for your data transfers. There are further approaches where you use memory-centric systems where you perform computations in your main memory, and then now it will be so you have reduced these data movement, but you will still have the data movement from your storage to your main memory, for example, your DRAM. Now, for this external IO bandwidth of the storage system is now the main bottleneck for these memory-intensive applications. Now, there are another class of processing paradigm, which is storage-centric system, where we perform computations inside this SSDs or storage or general storage systems, where we fetch the data out of your NAND flash memory, and then we have some computation unit inside your SSD itself so that we can perform computations. But still, there are channels that you have to perform computations so that they can be the next bottleneck for you, so that because they will be limited how much data you can transfer. So now this limited internal bandwidth of NAND flash chips becomes your new bottleneck. Now, with this, we go to our second key problem, that data movement is a major bottleneck in different processing paradigms, even in storage system, for example, in storage processing, for reading these large encrypted databases stored in SSDs. Now, there are prior works which reduce this data movement even further after using in storage processing. So in flash processing enables computations inside your SSD by exploiting these operational principles of NAND flash memory, where you perform computations inside the NAND flash where the data is residing. So you don't have to transfer the data out to perform to where to perform computation. You can perform already inside your flash. Now we will look at it. I just give a glimpse that we can perform computations even not even moving the data inside your just flash chips itself. So with these key problems and these things in our mind, our goal is to develop. We want to use in-flash processing so that we don't use data movement, and we want to perform a very functional algorithm which can eliminate, or let's say reduce, the homomorphic multiplication operation. So we develop our goal is to develop an in-flash processing based algorithm hardware co-design system that can perform scalable, parallelizable, and efficient secure exact string matching. Now we will look at exact string matching. Basically, we are looking at, and prior works they have used Hamming distance to calculate exact string matchings, or using Boolean approaches. Can we do better? Now let's look into the key idea, what we do so that we can improve on these works. Now the key observation is that, for example, you have your database, you have your query. Now, if you negate your query, I'm talking in general conventional system. If you just negate your query and then send it and perform additions of these queries on your database, the result will be whenever the query matches actually. Now the negated query will be actually just the replicate of your data, so that the addition will be a string of ones. The carry will never be propagated because it will be always, there will be no carry because it's always the replicate. Now that's a string of ones. Now, can we actually generate a string of, so in conventional system, what I can do is also send a string of ones and then just match where the strings of ones comes. And then we can find that our match exists, our query exists. Now, this is in conventional database system. This observation can be also extended to perform secure exact string matching using homomorphic operations and homomorphic addition. We perform addition there. Now we perform homomorphic addition. For example, you have homomorphically encrypted database. You encrypt your query. So for example, first, again, the same procedure, you negate your query and then you encrypt your query and then send this encrypted query. And instead of addition, you perform homomorphic addition operations. Now, when you perform homomorphic addition, the result will be actually a homomorphic encryption of 1111. Now, can you match somehow, create this encryption of 1111? That's the earlier question that I got also, that how will I actually find the match? The encryption of database will be some value, let's say A1, E1. Encryption of query will be with some value A2, E2. How will this encryption of 1111 will be generated so that I can actually match, find that it exists? That's something that we will look at now, how the algorithm will work. Yes.
This encryption technique is kind of associative, right? So So there's a proof for this, right?
Yes. So basically, when we go into the details of it, what actually happens is after in encryption, you actually just basically have this E1, which we discussed earlier, E1 and A1, they actually go either multiply or add. Now this E1, E1, A2, E2, everything is something which is known on my host machine. I know those values. Similar, so based on that, can I construct how, based on the, let's say, associativity of these A1, E1, A2, E2, can I construct the encryption of 1111 so that it actually becomes exactly what I want to match? That will now convert an homomorphic encrypted match into a conventional string match, where the encrypted value to encrypted value, if the both of them are same, then I have the basically my match. So that's what we are going to see in our later slides, how we do that.
Yeah, but my question was about like encrypt of query, adding
Plus
encrypted of your negate.
Yes.
It's gonna be encrypt of 111. So that means your encryption function is kind of associative.
Yes, it's exactly. So that's what I was just going into more details of how this encrypt of these things look like, which is basically what we want to do is A1, E1, A2, E2, what we discussed, and they are also associated, and that's what we use basically. Yes. Anything else? Any other questions? Any questions on YouTube? Okay. Okay. So now with this, our key idea is that for performing exact string matching, because addition now is working for your exact string matching, we use only homomorphic addition to perform our secure exact string matching. That's our first key idea. Now, homomorphic addition is highly parallelizable. Just by we are discussing, we have polynomials. Homomorphic addition is itself a polynomial addition. Now, what polynomial addition means? Take individual coefficients and just add them one by one. It means it is highly parallelizable. So basically, we can exploit the inherent parallelism in NAND flash memory, where we have a huge array level and bit level parallelism from the NAND flash memory. And then we improve the performance of this secure string matching, our whole application, secure exact string matching. And once we perform our computation in a bulk manner, using the inherent parallelism of NAND flash memory, we also reduce the data movement. So this is our second key idea, that we use the in-flash processing. So we reduce the data movement also, and then we utilize the inherent parallelism so that we can perform homomorphic addition in a wide SIMD NAND flash bit lines, for example, which we will discuss in more details in our mechanism. So the second key idea is to use in-flash processing to reduce data movement, and then we accelerate secure execution. Now, with these two key ideas, we propose CIPHERMATCH, an algorithm hardware co-design, which improves the performance of HE-based secure exact string matching by reducing memory footprint, where we optimize the data packing scheme, what we talked about earlier, that we can pack one bit in one element. We'll see now everything is changed. We just need to do addition. Can we pack even more? So we'll see how we can optimize this data packing scheme to pack even further. We will eliminate the costly homomorphic multiplication operations, because we are now using only homomorphic additions. And then we reduce data movement, because now we can use this homomorphic addition, which is a much simpler operation, and support this wide, and then can be accelerated using this wide SIMD lanes, so that we use our proposed in-flash processing architecture, and then we accelerate the secure exact string matching. Now these are the outcomes of the CIPHERMATCH proposal. Let's look at CIPHERMATCH from a system overview on a high level, how it looked like, and then we'll go into the parts of it, how the algorithm works and how the hardware works. So as we discussed earlier, also we'll assume a client and a server machine. We'll have a client has its database. It's again going through the same we discussed earlier, that we efficiently pack this database, because now the application function has changed. We don't have to calculate Hamming distance or homomorphic multiplication. We just have to perform homomorphic addition. So we efficiently pack this database, which reduces the memory footprint after encryption. We'll see later. We store this encrypted database into the storage system. Then next, the client has query, and client will also pack this query to perform this parallel string matches on this encrypted database. We send this encrypted query. Then we perform secure exact string matching using only homomorphic addition. And to overall accelerate this, we can perform these computations inside SSD again by using in-flash processing. So we'll see all these points, and these all points actually converge to 3 key steps. First is to have a memory efficient data packing scheme. Second, to have an exact string matching algorithm from additions that we looked at. And third, in-flash processing. Let's look at these key steps one by one. So first we'll move into CIPHERMATCH algorithm, which constitutes of the first 2 key steps. Let's look at the first key step, how we look at memory efficient data packing scheme. Now, let's go back again to our example from our key observation. Let's see how we'll pack it. So we have a query, we have a database, for example. Now, if you zoom our database like this, in the prior approaches, or in the example, we saw that we'll take chunks of it, we'll take each bit and put it into the elements of our vector. Now here we take multiple of bits and place them into the elements. Now, as you remember, this box was one element. Previously, we were placing only one bit. Now we are placing more than one bits. That's what overall we discussed right now. Why we can place more bits is something, because now maybe you can relate here. I will come to that again, but to give a glimpse here that we have this encrypted database. We have query again like this. Homomorphic addition means performing addition between these elements. And that's what we wanted to do initially from our key observation, that we wanted to perform additions. So we can pack as much bits as possible here, which are provided by homomorphic encryption standards, so that we can actually get the max out of it, and we can pack maximum as possible. Now we encrypt it. Now we will see how exactly this associativity looks like. So we encrypt this database, for example, D, with parameters A1 and E1, and we call this as an encrypted database. Now here, what we will see is we are packing instead of 1 bit, a 16 bits. And again, in the plain text, if we have 1024 polynomials, we can have for sure more. That will improve the performance even further. Once the 16 bits actually converted to 32 bits after encryption, and we have 2048 elements, and we see an overall, as compared to 64x growth, we will see now only 4x growth. Now there is a thing that we need to notice, is that prior works actually, whatever we have seen, they actually use Hamming distance to calculate. Now Hamming distance can also be used to calculate approximate string matching, which is actually also used in many applications. Whereas this approach only supports for your exact string matching, because now everything has to be done with addition. So, but we specialize for an application, or let's say an algorithm which is secure exact string matching, and for that we can actually reduce from 64x a memory growth to only 4x memory growth. So that's what we observe in this overall memory efficient data packing scheme, specifically for secure exact string matching. Yes.
So if you want to do multiplication with packing 16 bits,
yes,
what do you need to do?
So actually you can do multiplication, but that will not give you anything related to your string matching operations. This packing scheme is actually used when you have to perform your machine learning operations, because in that you have like 8-bit or 16-bit values that you need to multiply. So you pack like 16 bits, you can multiply that value. That will give you for other application, but for string matching, it will not be helpful for you. Any other questions?
And why are you packing 16 bits?
So this is coming from the homomorphic encryption standards. We are using a 1024 element, like polynomial degree of 1024 elements. You can actually go up to only 16 bits that you can pack. And this is called as plain text modulus. So you can only go in one coefficient, you can only pack 16 bits. It should be basically only 16-bit value. If you go with 2048 element, it can actually go higher and can go up to, let's say, 32 bits or 34 bits, for example, based on different schemes.
So is it a random threshold, or is it something like there is a theory back?
There is a theory back, and on this back, like for example, why do we use this specific? So generally we want to use this elements like polynomial degree of 1000, like 2 raised to power, and they has to be very large. So first we define actually the threshold that it has to be larger than this value to provide the security of homomorphic encryption. Then the second thing is, if you can take any arbitrary value, that will be more complicated for your hardware. So that's why you use 2 raised to power, let's say 10 or 2 raised to power 11, 12 values, so that you become more hardware friendly while performing these operations. And then the third is basically these bit values, which also comes specifically, there has to be a prime number that we choose so that they actually go much better while performing computations. For example, polynomial multiplications, or we talk about FFT or MTT. There has to be prime number specifically so that we can perform them.
16 is not the prime.
No, so these are bits, 16 bits. So the value that actually has to be 2 raised to power 16 is a value. You choose a prime number, which is actually around that 2 raised to power 16. And the value, the value of this should be less than that. So actually you can take 16 bits and pack it. Any other questions? Okay. So now we have our encrypted database or packed encrypted database. We'll take our query. Now let's see how the query should look like. First, we have our query. We negate our query. We have a negated query. Now we want to perform, we saw that we want to perform additions in the conventional domain. We will encrypt it, but it will be good if you can perform additions over your database in parallel. What can you do simply is that you replicate this bit across, replicate this basically query across your multiple coefficients, so that individual basically with your database and your query, it will be all parallel addition. So you will perform in parallel and in bulk for your query and your database. Now again, we encrypt this negated query with the parameters A2 and E2, and this is our encrypted negated query. That's how it looks. Now we encode this query by negating and replicating into the single plain text vector, basically this plain text, or say the first this part basically, where we replicate this and then we perform encryption. Now we have our database, we have our query. We will look at now next thing, how will we perform string match. We have efficiently packed it by only having 4x improve. So from 64x we have improved to 4x, but specializing for an application for secure exact string matching. And now we'll look at how the secure exact string matching algorithm will look like. So we want to perform addition between these two, and it essentially means just the addition of these individual elements. So once we do that, it essentially means that database plus encrypted of query will be a result. A1 and A2 will be A1 plus A2 in your mathematical function in your encryption. E1 and E2 will be E1 plus E2. Now this is how your result looks like after addition. Now this is the result encrypted. I don't know anything yet whether the match exists or not. But we decrypt it. When we decrypt it, for example, we are not decrypting it on the server or anything, but let's see if we decrypt it, we'll observe that this here is actually, we find a match where exists a 1111 value. Now we don't decrypt it in the cloud server or let's say any other third party, because that's just remove or eliminates our overall goal, what we want to do by performing on homomorphically encrypted data. So we want to find the match on this encrypted result. How we will do that? So we will define a match value where each coefficient, each element of the vector will actually contains a 1111 value. Now when we encrypt it, we encrypt this MV match value with this associative parameters A1 plus A2 and E1 plus E2. And why you can do it? Because I just assumed and explained with one example that A1 is with me, A2 is with me, E1 is with me, E1 is with me, because I encrypted the database. Now I am sending the query. So once you do that, you have this encrypted value, which will be with these parameters. And once you have these parameters, they are going to be actually, as you can see, 53 is here. So if 111 exists in the result, this will also be encrypted value, same as 111 of what we have generated. So we'll compare just directly. This is a just direct comparison how we will do. And then if you compare, you see 50, 50, 53, 53, you actually found a match. That you have a match. You send basically whatever you want to send. For example, your index, your final result, for example, yes or no, back to the client, where you want it. So just to summarize back again, we have our efficiently packed encrypted database using a memory efficient data packing scheme. We have negated replicated query and packed query, basically because we packed it across different elements, and we also send an encrypted match value along with that query based on your parameters A1, A2, E1, E2. It can change. Encrypted match value will also change with the parameters. And then we perform string matching using only homomorphic addition. So this completes overall how the algorithm works at a very high level. Yes.
One question. Do you send if the match was found or not, or do you also send the index?
So it depends on how the application looks like. We can also send where the actually the index where in your database the value has matched. We will send it back. You can send it.
And if you send that, then is it constructed in plain text and sent in plain text?
So right now, whatever I have explained is constructed in plain text, but I will come back again to a discussion that how exactly can you improve this further. Okay. So I will do that discussion in just after completing this. Yes. Any other questions? Okay, now let's move on to our hardware design. Now we construct everything with homomorphic addition. Let's see how it should design our hardware. For example, we want to perform secure exact string matching inside SSD using in-flash processing. So we will now look into more details. What we should do so that we can support that. So let's dig deep into the overview of a modern SSD. So modern SSD has a SSD controller, which is a general purpose port, and it is connected with the flash chips which exist at the back end of your SSD system. And we have an internal DRAM where we can buffer the intermediate data so that the data sent out from the flash chip can be buffered and then can be sent out, let's say, for example, to your SSD controller or outside your SSD. Now, inside each flash chips, we have multiple dies, and in each dies, we have our data which is stored, and it is where we actually have our NAND flash cells. There is a further even hierarchy that there are inside. So we have multiple flash chips, we have multiple flash dies. Inside that, we have multiple planes actually, and then inside those planes, we have our NAND flash cells which actually constitute our data. So you can see actually we have a lot of parallelism coming on, and then we will see how the inside itself in the NAND flash memory, we can also exploit further parallelism. So let's look into a bit more detail how this NAND flash memory will look like on a very high level. That in the NAND flash memory where the data one will look like, this is known as data A1 is represented. This is known as block. And inside each blocks, we have multiple word lines and multiple bit lines where they store actually 1 or 0. Now, how 1 or 0 is stored is basically 1 represent the erased state. Basically, we have a NAND flash cell and we either program it, or basically we can program it so that we can store our data 1 or 0, and then we perform the current sharing, and so that we can read out what exactly is the value stored in that NAND flash cells. So 1 represent an erased state where you can basically erase your cell that represent 1, or you can program your cell that represent a 0. And when you program your cell, it actually means that it acts as an open switch for you so that the current cannot actually pass from an open switch. Whereas when it is erased, it actually operates as a resistor. So these are just going into very brief details how a NAND flash cells actually operate on. Now, just going back again to our overview, with these NAND flash cells, we have to, so again, with some circuitry, we have to perform current sensing and all those operations. For that, we need to have some sense amplifiers to fasten these operations, and that's why we have sensing latches and multiple data latches so that you can store these data, whatever you want to read out from your NAND flash memory. Now, prior works have shown that you can use latching circuit to perform computations, but they are restricted by performing only bitwise operations. Now, these are the limitations of prior work. You can perform bitwise operation, but what we want to do is addition, homomorphic addition, which is addition. So we need to actually improve this work so that we can perform addition. So as just again rephrasing back, homomorphic addition can be parallelized and we can exploit bit level and array level parallelism. Let's look into a bit more details of how a storage system will look like. Even going in further on the storage system where we perform the string matching. We want to perform homomorphic additions inside the NAND flash where the database is stored. You basically send your query. So the query should be gone to your NAND flash array. It should perform your homomorphic additions. Once you have generated your result, it should be given out, and then your index should be generated so that you can finally compare. So you can compare it with your match value, and then you can finally send out the final index, or let's say result back. Now let's look at one by one. So For homomorphic addition, we perform element-wise addition and look at how we will perform element-wise addition with our third key step, which is our proposal for a new in-flash processing architecture. So we use bit serial addition because you have vertical bit lines. You can actually perform those in bulk so that you avoid carry propagation, and then those will be very wide SIMD addition operations. So we had our database, what we looked at. Each element was basically multiple bits. You basically lay out the data vertically now in your NAND flash. So your data was like in your coefficients, the bits, you actually place the bits vertically in different bit lines. Now let's look at what are the operations we perform in the single bit line, and let's look at, and that will actually be scaled out to multiple bit lines. Now just to remind back that there is a sequence of operation which will go into, but just to remind back that we have our flash cell, we have a latching circuitry which constitute of a sensing latch and a data latch. So these actually can store values for you. And for our commodity SSDs, we actually have available one sensing latch and multiple data latches, for example, up to 3 or 4 data latches for you. In this example, we are showing three latches for us. That was efficient enough for us to perform our addition operations. Now let's look into this latching circuitry a bit more detail. I will go through it, not into details, but this is how a NAND flash latching circuitry will look like. You have bit lines here, and then you have sensing latch and data latches for you. I will not go into minor analog details of it, but you can assume that they are connected with each other by a transistor circuit, and this transistor circuit is again directly connected back here. And this is how our sensing latch and data latch looks like. Now, on this, can we perform bitwise AND operations, bitwise operations, for example? They are proposed by prior books, but we need to use them efficiently by basically converting your addition operations into these bitwise operations, data transfers, and somehow between these latches. So let's see very simple how bitwise AND of A and B will look like. First, you read the data from your, let's say, NAND flash cell. You store it into sensing latch. You transfer the data from this S latch to D latch. You actually transfer similarly in another data B. You can actually read it, but in this case, what we have to do is query sent from outside. So we'll send the query from SSD controller to the NAND flash, and we'll store it into the sensing latch. Now we have our sensing latch and data latch constituting values B and A basically. Now let's see how the bitwise AND operation between them looks. Assume the data latch was storing a value 0. If you precharge the bit line, now these M7 and M8 are the transistors that we will control. Now, if we control this M8 transistor and we enable this M8 transistor, the M7 transistor will turn off because the value holding in the D latch is actually 0. Now, this means that the bit line will actually remain at 1. If it remains at 1, actually, because there is no discharging path from here. If this bit line remain at 1, this transistor will turn on. If this transistor turns on, it actually pulls down all the values and make it 0. Now that means that your D latch value is 0, your output is actually stored here, which is 0. Now, if you have a D latch value 1, which is present in your D latch, again you precharge and control this M8 transistor. What will happen is it will discharge now because there is a path. This is a 1 M7 transistor will be turned on, and there is a path for it to discharge. Now, once it discharges, it means that bit line will go from 1 to 0. And once it goes to 0, this transistor will turn off. And this means that whatever the value was here, it will be retained. So if you look at the truth table for the S latch, which was containing a value B, and it propagates to the output, that is actually a bitwise AND operation between two things, A and B. Now that's how we do bitwise AND operation. Now similarly, by controlling the circuitry, we can perform further bitwise OR operations. As we just saw that we can perform data transfer from sensing latch to data latches. Inside NAND flash, the prior works have also shown that we can perform bitwise XOR operation, that there exists an XOR circuitry itself, so that we can utilize that for XOR operation. And then we use these operations to perform our addition operations. Now let's look at how we'll do addition. Yes.
So bitwise and or operations that you explained, these are not part of the contribution of CIPHERMATCH, right? These are from prior paragraphs.
So
like, did you modify also or not?
So so we can say that we actually used a different sort of so what the differences are is actually they assume a different set of this peripheral circuitry what they have, and what we used is actually this property of having these two more transistors. We did not add this transistor. This is actually observed in one of the prior work that industry added this set of transistors so they can improve their programming operations of NAND. Now we use these two transistors so that we can perform our bitwise operations, and we use these set of bitwise operation because we want a fine-grained control over where the data actually goes, where the result actually goes. So that is actually required so that you can perform addition. Any other questions? Okay. So let's see how our bit serial addition looks like. So we perform a bunch of operations because you can convert now your additions into bitwise operations and data transfer between these because you need to store intermediate results. And there are a couple of steps that are involved. So when we lay out the data vertically, we send from the SSD controller our query to this sensing latch. For example, your sensing latch. Then we perform a sequence of operations. These are explained in more details in our paper. You can check out that for more details. But just again, we are performing the bitwise operations in a sequence manner so that we can finally generate a sum bit and a carry. Now, once we sum it, we will actually accumulate the result over the sum bit so that finally we have basically the result. Now, we are also performing the match in our latches so that we can only generate the final index in our SSD controller, because SSD controller was a general purpose code. So we actually find the sum, which is actually homomorphic addition. We also send the next part, which is your encrypted match. We actually perform the encrypted match value and you will accumulate it. Now, once we accumulate it, if all the values actually match, which is just a simple XOR operations, you will actually see the output is actually 0 if all the values are same. And that's what we actually send out as an accumulated bit from the SSD controller, from the your latches to the SSD controller. And this now data is actually now further reduced. Instead of sending all the final result, you have reduced the data so that it's just the final bit that you just send it. And this final bit is now will be basically used to find out whether it's where exactly is the match has happened. We can generate the index from it and then can send it back to the client. Yes.
So you do this addition inside the flash memory, but then you also you need to do XOR.
XOR, yes.
Comparing against the
match value.
Encoding of the match value,
yes,
right?
Yes.
And then you need to send out the result of that XOR to the SSD controller.
Yes.
So basically, I get the benefit from the from the parallel, but I don't get the reduction here. You don't really reduce. What do you reduce?
So once you have, let's say, for example, your value, it will be generated bit by bit, right? For your addition. Now, let's say, for example, 4-bit number, which you have generated. You have an encrypted match value, which was a 4-bit number. The result is generated, the bit here. You will send that bit of that match value. If they are fine, you have the sum, basically. If they are the same, they will be basically 0. XOR of them will be 0. Then you have the next bit, that XOR of them will be 0, you accumulate it. So if you are accumulating this, the final result will be actually 0, right? For you, if both of them is actually the same.
I couldn't follow.
So for example, I will take a very simple example. For example, you assume a 1 1 1 1. You XOR it with 1 1 1 1. If the both of them are same, the output will be 0, 0, 0, 0, right?
Yes.
Now, if you take all those zeros and XOR them all together, this is a reduction that we are doing. The output should be 0, right?
Oh, you're doing that also.
You are doing that because we are doing bit by bit everything. So we have a controls over bit. So you do one by one in this same bit line itself, in the same bit line, one bit result, one bit XOR it with the result, one bit XOR it with the result, one bit XOR it with the result, so that the final bit should be actually 0 for you. That's how you can see that both the values are actually same. Now what we have reduced is instead of sending 4 bits out one by one, you just send only 1 bit out. That's the benefit that we have.
Okay. And how do you map your data in the flash blocks? So you said that we have this vertical layout.
Yes.
Right.
Yes.
So we have several blocks in the.
Yes.
So I can see that you put.
So for example, you put 32 bits in one block. You can have more bits based on the number of word lines that you have.
Yes.
And then this is in one bit line of 32 bits, you have one coefficient. And then similarly, you have multiple coefficients in multiple bit lines. And that you basically create a mapping of where exactly your homomorphically encrypted data stored into your address mapping scheme, which will be modified for this specific vertical layer.
Yeah. So my question is that is the number of word lines in a block or number of pages in a block, does that limit your technique somehow or not?
Number of blocks. So no, actually, because I was thinking in a way that you have, let's say, for example, 32. For example, you have 32, and in a block you have 64 word lines, for example. Now, what does it mean is that I can store 232 values, 32-bit values in a number of pages. But essentially, even if we divide the block into 2 blocks, the NAND flash right now currently works in a plane by plane manner. So you can actually operate on one block at a time in a single plane. So the results will actually remain same unless you can actually operate on multiple blocks parallel.
This is not completely correct. You cannot operate on 2 planes at the same time unless they have the same offset.
Unless they have
they have the same offset.
Yes. So if you are working around the same word line, yes. So basically, when you have when you consider 2 planes, you are performing additions of all the things parallelly. So if you can activate first word line.
No, assume we have 1 plane.
Yes.
So in 1 plane, but essentially the number of pages in a block is lower than the number of bits you need to put. Like for example, assume that you have 16 pages in a block.
Yes.
But your, I don't know what you call it, the coefficient is 32 bits. For example.
Okay. Yes.
So how do you? Basically, you need to put in this.
Yes, I mean you need to put it into the next block so that your data actually is there. But they all use the same sensing circuitry because along the word line there are multiple blocks, but they actually share the same peripheral circuitry which are sensing latches and data latches.
Yeah, nice. And the fact that you're not using, I think, Flash Cosmos. Multi-word line sensing. I mean, that enables you to basically go beyond the block.
Yes, that's true. So another work which this work we are actually operating in our latches. There can also be further possibilities that you can actually operate on inside using the analog properties of the NAND flash cells itself, so that you can perform some operations.
Yeah.
Yes.
Okay. Sounds good.
Thank you. Any other questions?
Mayank?
Yes.
If I can ask a question. So I understand that this technique sends an accumulated bit to the host saying that whether the data is present or not. But could you please give some examples of how, from the application's perspective, how does it know that the location of where the data resides in the SSD? So that part is something that we have not discussed in the work also. Like once you know that the data is available, how do you know where the data resides?
So actually, that's true. And the fact that we assume that when you will send this reduced result back to the host, or not to the host, to the SSD controller, where the SSD controller will have your mappings from where the data is coming, right? So we need to keep a track from which block or which page the data is coming, so that we can also, and then we need to verify it from our address mapping, so that we can say that from where actually the address is generated. So this is another thing that we need to do at the controller level. Did I answer this question?
So we are actually only looking at or trying to localize the search results within a block, let's say.
Okay, yes, that's true.
So, that's my question. So
That's true. Yes, I mean, so
Okay.
what we know at this point is that where exactly at which page or which block actually I am performing, and based on that, I know the mappings of that, basically what exactly is for example, we can maintain a mapping of our database that this is going into this block and this is the mapping of that data block. Now this mapping can be used, and these accumulated result that we have will be basically used so that we can generate our index, for example, that you have actually add match at this index. That's for basically if you want to send an index. If you just want to send a final value, whether it's a yes or a no, you just don't need to do all this. When you receive the data from the accumulated bit to the SSD controller, you can just search that if there is a match, because if the reduced result is 0, then it means you had a match, just send a yes directly. So that's the two things that we can do, and it can depend on based on applications itself. You can use index, or you need to generate something else which needs to that the SSD controller needs to have all these details. Yes.
One last comment point on this. So it still looks like an approximate search, because your result is not directly correlated to the data that is present in the word lines, right? So you still have to kind of you may know the block where the data resides, but you still kind of have to go and look at all the pages where you may find the final result.
But yes, but what we are looking at is like exact string matching across all database, right? So we will do it across all the database that we have, and then we will say that, okay, whether the exact string match occurs or not, right?
Okay.
Asking when you want to localize in which, I guess, block, and which page you have the match.
Yes.
I think you don't have that information.
So you need to maintain that metadata information into the SSD controller, so that once this accumulated bit is sent out, you can actually find that, okay, this result of accumulated bit was sent out from this block, and on this block, actually on which word line, oh sorry, not word line, bit line, we got that match actually. Yes.
So that accumulate. So usually for equally check, we need to do XOR, and then we need to do AND operation.
Yes.
Right? So you are doing these XOR AND, things like that. Right?
Yes. Yes. Okay.
That's how
we reduce.
You reduce.
Yes.
I was trying to understand where you're doing AND operation.
Okay.
Now I got it.
Okay. Then I will move on. Any questions on YouTube? Okay. Okay, so we have now this, I guess we discussed already on the second part, that we send out this accumulated bit and we generate the final index value. And then with this final index match, or let's say result, yes or no, we send it out. And we use the general purpose code, which they're the SSD controller, and we utilize this to identify the final match. Now, this is all about how our CIPHERMATCH system overview, how it will look like, and then how the algorithm and hardware part looks like. There are more details on how you need to modify your SSD so that you can support these things, but we are not going into details for that today. And you can check out the full paper for that. But we'll now move on to evaluation results. So we have our evaluation methodology in two parts. First, on a real system where we evaluate our algorithm, and then second is on a simulation environment where we evaluate across different types of processing paradigms, which we will look at. And we evaluate our software-based CIPHERMATCH implementation using Microsoft Seed library. And we evaluated it against two baselines. One is using arithmetic approach, one of the prior work, which was the best in terms of performance, and the one of the state-of-the-art Boolean approach, which was a recent work, which tried to look at these string matching operation, also using the TFHE Rust library, which is specifically for Boolean approach. And we evaluated across various query sizes actually, from going from 16 to 256 bit, for example, keeping your encrypted database a constant, or varying encrypted database where you stick your one size of query which is 16 bit, but you use multiple queries, for example 1000 queries, so that we can analyze how exactly is CIPHERMATCH performed. And for all the query sizes, we are assuming that for let's say 16-bit query, we can also find all circularly shifted queries also, so that we can actually perform all sort of variants of that strings or the query in our database. So we show speed up for different query sizes, where on y-axis we have speed up, and on x-axis we have different query sizes. For our analysis, we assume that Boolean approach is our baseline, which is set at y equal to 1, and we will observe the speed up as compared to this approach. So arithmetic approach, as we just saw earlier also, is actually shows a very high speed up, and it itself outperforms the Boolean technique by an order of magnitude, the prior arithmetic techniques. Whereas CIPHERMATCH software implementation outperforms this prior arithmetic technique by 42.9 times further. Now, this is because we have removed homomorphic multiplication operations and we are only using additions, and that's why we are seeing this much speed up. We also observe that CIPHERMATCH software speed up increases when we increase with query sizes, because when we have larger queries, you have to perform many homomorphic multiplication operations, because you have to take as we saw in our packing schemes, you have to pack one bit, and then you can actually need to go, even if you go beyond your ciphertext size, you have to perform even further, like more multiplication operations, which are much more costlier than performing more homomorphic addition operations. So that's why we have homomorphic, like we are seeing this increase because we have only using homomorphic addition operations. Now, these are the very brief analysis of in both the approaches and speed up across different query sizes. There are speed up for different database sizes, which is there in the paper, and you can check out that for more details. We provide more analysis into this software-based our real system methodology. Now let's look at our simulation-based evaluation methodology. So we need to actually evaluate our in-flash processing based CIPHERMATCH implementation, and we do that by modeling the characteristics of our NAND flash memory. We evaluated against baselines, 3 baselines, where we are running on 3 different paradigms. One is CIPHERMATCH on a compute-centric system. The configurations are same as what we use in real system. CIPHERMATCH running on a memory-centric system, where we used a prior work called SIMDRAM to perform the addition operations. Now we provide brief details about how we map CIPHERMATCH into the SIMDRAM framework, because SIMDRAM proposes performing bit serial addition, and it's the same that we discussed, that we can perform bulk bit serial addition operations, and we provide some details on how can we map CIPHERMATCH to the homomorphic addition, basically to the SIMDRAM substrate. And then finally, CIPHERMATCH on a storage-centric system, where we utilize the internal DRAM, which we saw in our overview, which is used to buffer the intermediate data. So we use that to perform computations. So you actually reduced your the external I/O bandwidth. You don't need to go now. You further go into your SSD and can perform computations inside that. So these are the 3 baselines that we have compared with. And again, we evaluated it for the same workloads for varying query sizes and varying encrypted database sizes. So again, going with speed up for different query sizes, we have again on y-axis speed up, x-axis query sizes. And in this approach, this graph, we put our CIPHERMATCH software, the compute-centric implementation, as y equal to 1. And then we'll see the speed up of other approaches on top of it. So all three other systems, all three other paradigms, the memory-centric, storage-centric, and our proposal in flash processing actually outperform the CIPHERMATCH software implementation, the compute-centric implementation, by reducing the data movement, because you don't have to go through the limited channel bandwidth of all those channels between your DRAM to compute or the storage to DRAM. We also observed that CIPHERMATCH in flash processing outperforms the CIPHERMATCH software on average by 136.9 times. And CIPHERMATCH IFP outperforms other near data processing systems also on average. Now, there is another interesting observation is the fact that now CIPHERMATCH IFP speed up actually decreases with these query sizes. Now, this happens because we are looking at the circularly shifted queries. Now, what does it mean is that you have to take the query and you are performing bit by bit on your NAND flash. So you have to read for one query all the bits, and for all the circularly shifted query, you have to again read it. So you actually do repeated flash operations, and now flash read operation. Now flash read operations are much more expensive, in order of microseconds as compared to a DRAM read operations. And that's why we observe that with increasing query sizes, we are actually seeing that the speed up decreases. And even for 256-bit, we observe that CIPHERMATCH PUM, which is processing using memory, SIMD-RAM framework, is actually performing better, slightly better as compared to CIPHERMATCH IFP, which is because once you can actually take the data, load the data, and then you can perform faster DRAM read operations. And then, so this is you can actually perform like faster DRAM read operations because you have to perform redundant or repeated DRAM reads, but they are still in order of nanosecond as compared to flash. So this is our observation for different query sizes. We also provide observation for different database sizes, and we provide an individual comparisons between all three approaches or all four approaches in more detail in our paper, how the trade-off is looking like across different paradigms for this specific set of applications. We also observe the energy consumptions. We model the energy consumption, and the CIPHERMATCH software again set at y equal to 1. And we observe that near data processing systems, all near data processing systems, for example, memory-centric, storage-centric, and in flash processing, they provide large energy savings over CIPHERMATCH software implementation, where CIPHERMATCH in flash processing provide 256.4 times energy savings over CIPHERMATCH software. And this is because you largely reduce the data movement. You're performing all the operations inside your NAND flash arrays. As I said, there are more detailed observations from our evaluation in the paper, an end-to-end system design. How can we enable CIPHERMATCH and commodity SSD? What you need to modify for your in your firmware, in your or any hardware modifications, what you need to provide. We provide an overhead analysis of CIPHERMATCH hardware that we propose, the modification, a bit modification on your peripheral circuitry, and the storage overhead that we need to use, that we need to have, and then in detail how bitwise operation are performed. And you can check out our full paper for more details. So to summarize, finally, we have CIPHERMATCH, a new algorithm hardware co-design that significantly improves the performance of secure exact string matching, where we pack multiple bits of database and eliminates the use of homomorphic multiplication, which gives you reduced memory footprint and provides scalable, secure exact string matching. On the other side, we use in-flash processing to accelerate secure exact string matching, which reduces data movement and leverages bit level and array level parallelism. And finally, we show that both CIPHERMATCH software and CIPHERMATCH in-flash processing outperform the state of the art. So this is overall that I have as a conclusion. Is there any questions? Any questions? Okay. So now I will move briefly into some discussion that I had quickly. That as we have seen that we just discussed about my database, for example, the user's database and encrypted it. I know all the A1, A2, E1, E2, A1, E2, A2, E2 values, and we saw that how can we perform those the encrypted search. Now, where all these techniques can be, where all this CIPHERMATCH proposal can be applied in all other paradigms, all other, let's say, contexts. Can you think of some things? We discussed about a single user system where we have a single user that stores the database. What can we think more? We just need to know A1, A2, E1, E2 values. Can it be applied to another type of context? Maybe any other application. Maybe I'll give a hint for multi-users or organizations. They can also, can they apply these things?
There we will have to make sure that they all have access to it.
Yes. So this is like, if you have a multi-tenant cloud system, for example, like you have, for example, you're an organization, you have your database stored in an organization, and there are like multiple users which you know. Now, all those users actually need to know how this data has been encrypted, so that because they are trusted in the same organization itself. So you trust that, okay, if an organization provides you with their specific, let's say for example, the organization system. Now the organized system can be embedded with the values A1, E1, which how it's encrypted. And now whenever the user is sending his query, he's always encrypting it with A2, E2, A3, A3 or other things, all the users with different things. But they know the A1, E1 value, and they can actually generate this encrypted match of 111. So this is where this can also be used. That's what I was saying. There can be other use case, for example, edge computing, because we have not explored these applications, but we have reduced the data footprint, the memory footprint from 64x to only 4x. And maybe this can be used from an edge device, where the edge device actually store this encrypted, store the data, encrypt it with this efficient data packing scheme, and then can send it all to the server so that it wants to perform string matching. So that's where it also can be used in a edge computing scenario. So these are all I have. We can you can even tell if you have even more scenarios that you can think of. But this is a general approach that we discussed. This can be applied to many contexts, not only limiting to a like a user or a cloud system. Maybe some other applications also can be used.
So I didn't get this edge computing.
Yes.
Can you explain?
So this is actually edge computing is a subpart of your single user system, and why we actually say this is that we reduce the memory footprint so that you don't strain on your bandwidth, so of like the amount of data that you need to generate to send it to the client system. So it is possible that you make it real so that your edge computing supports this kind of an encryption or data packing so that you send it to the cloud. Because now you pack the data more efficiently, you don't need to have so much of storage in your edge devices so that you can encrypt and store it by 64 times growth. It's just only a 4 times growth. So that's what, but I agree, it's a sub part of the first point, where you use a single user system. Yes. I'm just thinking of a different context.
Yeah, another context.
Yes.
And the problem, the limitation is not only the packing. Is not on like the memory footprint. It's also the computation power, right?
So the computation power, because now you at the edge device, you just need to do encryption, and that can be actually supported with a encryption module itself. Because nowadays in your edge devices, you're coming with your encryption modules, for example, secure embedded hardware. Instead of having a conventional AES based secure hardware, can you put a homomorphic encryption software? And that can help this solve this problem. Next. Okay, so I will now quickly.
Mayank, if I can ask a question here. So, can you comment on the generality of the CIPHERMATCH IFP technique in systems where they use a different kind of encryption mechanism, like searchable encryption? So, how does it work? Or can we take parts of this technique to those kind of systems where encryption is a mechanism is different?
So that is actually, I would say, because I would say it in a very general way, because the encryption scheme, homomorphic encryption actually supports you to perform computations, whereas other schemes does not support you to perform computations. Now, searchable encryption is another thing where you encrypt it with a conventional encryption scheme and then find a match. And conventional encryption scheme, for example, AES. Now, if those operations involved to find a match can be performed using this in-flash substrate. For example, we looked at only performing addition, but if your substrate can perform multiplication or other sort of comparison operations or data transfer between multiple bit lines, then yes, for sure, it can actually do that. But right now, it can limit, this substrate can limit the set of applications that is looking at. Yes.
Okay, thank you.
Okay, thank you, Rakesh, for the question. So I will now quickly move on to second discussion, and I will quickly wrap it up. So we look at CIPHERMATCH, which at the specific, which is an exact string matching problem. Can we enable more complex, for example, approximate string matching? For example, other sort of function, Euclidean distance, or some other functions which are used in the string matching, approximate string matching domain. Now we have several questions to answer this specific problem. Now, can we efficiently perform conventional approximate string matching by minimizing the use of complex operation? For example, the multiplications operations which we minimized and we reduced at the exact string matching. But can we somehow modify our approximate string matching algorithm so that it does not use multiplication? It can be performed with additions somehow. I'm not sure, but these are like some of the points that we can consider for future, that okay, can we do some sort of a different sort of packing schemes that we can enable this. Then second is, can we map these new algorithm that we proposed, which eliminates multiplication, and let's say it's used only additions or rotations or shifting, and then can we map this algorithm efficiently to conventional HE operation? Now there are different parts. For example, if you have a reduction, you cannot efficiently map it into homomorphic operations, because once you have data in your each cipher, each coefficient in your polynomial, you cannot actually perform a reduction of these coefficients. They have to be in separate polynomials. So that's another thing that we need to consider. The third part is, can we utilize these existing in-flash processing design? I think we asked about the generality of this proposal, CIPHERMATCH. Or we need to propose new or more generic computing, or for example, more generic storage-centric computing. Maybe possible. We looked at the limitation of prior works which only perform bitwise operation, and we extended it to perform addition. But there are recent works also which come in parallel with CIPHERMATCH that they propose to perform other operations like multiplications or shifting by changing the architecture of NAND flash. And can we utilize those multiplication and shifting to propose these or support these homomorphic algorithms? It will be an interesting to observe that how will these circuits or architecture will change, or maybe a mix of both things, like how we propose in CIPHERMATCH, the only final index or the yes or a no result was generated in storage controller. Maybe more things can be done in storage processing, or you use a mix of things to do different things inside your storage, because the storage is capable of doing many things. So these are the questions that we need to answer. And if we can answer, we can get some new applications which can map it. It will be very interesting to look at those applications. Yeah. And I will just lastly go with the third discussion point. I think this was something that was already asked. This is my last discussion point. That once in CIPHERMATCH, we actually send the result back to the plain text format. For example, what we have looked at, we have a discussion in the paper, how can we improve it further? But right now we looked at, okay, we just generate the index in our SSD, we send it back, or we have a yes or a no, we send it back. Now, is it possible that with this result, whatever you have sent, yes or a no or an index, can it expose some privacy issues? Can you think of something? With a yes, let's say you find a match and you're receiving a yes while coming to your user, And in the middle, you got to know that it's a yes, or let's say index. Can it lead to something? Maybe not the exact value of your ref or of your query, of your data, what is exactly, but your result is there. So this needs to be answered. Can you think of something? Maybe somebody don't want to expose that they have a yes result there or a no result there, because you don't know the query also, so you don't know the context of application going in, but you just don't also want to know what is yes. So we discussed in the paper that to hide this part also, we can actually use inside your SSD, there are encryption units which are present. For example, they use AES units so that they are used for encrypted data and store it into the SSD itself, where the data is at rest and you cannot steal the data. Now we use the same encryption inside the storage so that we can encrypt this data using a conventional AES screen and then send this data like yes, encrypted of yes, which is from AES, and send it out and back to the client. Now in the middle, you cannot have any attacks in the middle, so that you figure out it will be just encryption of yes. So you will not get to know whether it's a yes or a no. So I was just discussing what are the potential solutions that you can encrypt this result and in the SSD and send back to the client. We encrypt the result inside the SSD itself so that you don't have that vulnerable IO channel between your storage and your DRAM also. But there can be another questions that storage knows the answers. So somehow if you hack storage, if in future you can hack your storage system somehow to leak the data of your yes or a no, can we do even better? So you can also provide some obfuscations or a randomization while sending the results. So instead of sending a yes, let's say where you know that this is the match value that has happened on the database. It is homomorphically encrypted. You send that whole chunk of not whole chunk of database, but that part of homomorphically encrypted database, let's say one ciphertext, back to the client. Now this is homomorphically encrypted. Nobody knows. Cloud, even SSD does not, cloud system does not know, or the server system, that what is it. Inside that, even SSD does not know what exactly it is, because it is homomorphically encrypted. You send it to the client, and then basically client actually decrypts that result, because he can decrypt that result, and then we'll see, okay, this result is where I have actually the match on that decrypted result. So that can also happen. There can be further techniques or maybe other techniques that can be proposed, but yeah, maybe if you have any other suggestions, we can discuss on that. Otherwise, this is the whole my end of my talk. Thank you for all the brainstorming, all the questions, and
Any other questions do we have from the audience here? Any question from the audience in Zoom? It's the last chance to ask Mayank. Okay, going once, twice. Okay, no one. Okay, then maybe we can thank Mayank for the presentation.
Thank you everyone for the questions. It's an exciting topic to work on, and there should be many more things needs to be done in privacy enhancing technologies, not only restricted to homomorphic encryption, but many more things. So yeah.
Thanks, Mayank.
Thank you.
And whoever is joining online, stay tuned for future seminars from Safari.